So shall we begin?
Yeah, can you just give me 2 minutes?
Yeah, sure.
Hi everyone, I'm ready. Let me just share my slides. Is it visible
Good
now?
afternoon, everyone. Welcome to the second talk of Quarks to Quasars, a series of talks on physics and astronomy presented by Horizon IIT Madras. Our speaker, Professor L. Sriramkumar, is a theoretical physicist working in the Gravitation and Cosmology group at IIT Madras. Professor Sriram completed his PhD at IUCAA Pune and has since been working on topics of interest ranging from the cosmic microwave background to semi-classical and quantum gravity. Apart from his obvious love for physics, Professor Sriram is also an avid reader and an art enthusiast. His opinions on cricket are probably echoed by most of you tuning in, as he feels there is no other game like it. Considering that, Professor Sriram, how did you cope with yesterday's sudden announcement?
Well, it was bound to happen. it was due, I thought.
Yeah, we all knew it somewhere, but again, it was a very sudden and abrupt thing.
Yeah, I was hoping that we will get to see him, for Chennai Super Kings before he retires.
Yeah.
That couldn't happen because of the current situation.
So, shall we begin, Professor?
Absolutely, I'm ready. Let me begin by thanking the Horizon Astronomy Club of IIT Madras to give me, who have given me this opportunity, to talk about our work. This is a work that I have carried out with some of my graduate students here at IIT Madras, and I'm always glad to speak about work on cosmology here. Inflation refers to a period of accelerated expansion very soon after the Big Bang. It was invoked to overcome some of the difficulties associated with the so-called hot Big Bang model. Inflation requires negative pressure. It cannot be driven by ordinary matter that you and me are made of, or it cannot be driven by radiation, both of which are present all around us. It requires scalar fields, and there are many scalar fields in high energy physics, and then one invokes one of these scalar fields to achieve inflation. However, there are many models of inflation. Though cosmological data has improved tremendously over the last couple of decades to rule out some of these models, many models still remain viable. And also, there has been recent efforts which suggest that inflation may not be consistent with theories such as string theory. And there are other arguments which suggest that inflation may occur at low energies. You will eventually understand what I will refer to as low energies. Given the situation, we have felt that it is important to explore alternatives to inflation. The so-called big bounce is possibly the most popular alternative to inflation. In these bouncing scenarios, the universe goes through a phase of contraction. It comes to a certain small size before it begins to expand. And one can overcome some of the standard problems associated with the hot Big Bang model in these big bounce scenarios as well, just as you do in inflation. But the challenge is to construct a well-motivated bouncing scenario which is consistent with the observations. On the slide here on the left, it is supposed to be a representation of a Big Bang where there was a huge bang and the universe expanded. It cooled down as it expanded, as I will describe very soon, leaving some imprints on the cosmic microwave background anisotropies. I hope all of you are able to see my mouse on the screen. And then it eventually led to the formation of galaxies and clusters of galaxies. In contrast, on the right, you have something representing a big bounce. There was a universe which extended to past infinity in time, possibly. It shrank in size, so to say. And then there was a big bounce, and the universe began expanding, leaving its imprints on something called the anisotropies in the cosmic microwave background, which I will discuss in due course of time, and eventually forming the structures. The question is, can one construct well-motivated bouncing models which are consistent with the observations? This will essentially be the theme of my talk. Here is a plan of the talk. As this talk is aimed at students, I will spend a lot of time, probably close to 20 odd minutes, explaining what the hot Big Bang model is. And then I will explain why we require the inflationary paradigm. And then I will present the essential arguments about the bouncing scenario. I will also highlight what are the difficulties faced in constructing bouncing scenarios. And towards the very end of that part, I will also highlight some of the work we have carried out in this direction, and I will close with an outlook. So the Big Bang model is very popular. This is the screen grab from the theme song of the recent American sitcom, The Big Bang Theory. I know it's popular amongst physics students. And the first sentence of the title song, the title song starts with this statement: our universe was in a hot, dense state. In the first 20 minutes of my talk, what I will try to do is help you understand why we believe the universe began in a hot, dense state. What I want you to appreciate is that this is a talk on cosmology. In other words, we are interested in the physics of the universe as a whole. We are interested in the physics of the universe at large scales. We are not interested in a galaxy here or a galaxy there. And in this picture, which is one of the deepest views of space in the visible region of the electromagnetic spectrum taken by the Hubble Space Telescope, you see an amazing, bewildering, variety of galaxies of different shapes, colors, and sizes. We are not interested in the physics of a galaxy or even a small cluster of galaxies. We are interested in the physics of the universe on suitably large scales. Over the next couple of minutes, I will try to explain what we mean by the sufficiently large scales. Of course, in order to explain how the universe evolved, how it came to be, the way it is today, we need to know what the universe contains. In order to do so, we need to carry out a survey of the universe. Over the last 3 decades or so, many such surveys have taken place, and the Slow and Digital Sky Survey is one of the most ambitious surveys, one of the largest size surveys. It has, looked at, observed more than almost 1 million galaxies or so, and it gives us a feel for the distribution of galaxies in the universe. In fact, the SDSS team has created a nice movie, which I'm going to play for you, which will help you understand the distribution of galaxies in the universe and what I mean by when I say we are interested in cosmological scales. There are a couple of points I want you to appreciate before I start playing the movie. I will need a minute or so to play the movie. Firstly, it is very difficult to carry out a survey in all directions of the sky. So the SDSS identified certain directions in the sky to observe galaxies to the limit to which its telescopes allowed it. And secondly, in the movie you will see there will be 2 grids in yellow that will appear. The first grid is at a distance of about 1 million light years, and the second grid is at a distance of 1 billion light years. I hope, as being part of an astronomy club, you would have looked at the night sky. One of the, relatively bright objects, provided you go away from the polluted sky of the cities, is something called M31, which is the nearest Andromeda galaxy, which is located at a distance of 2 million light years. Often in cosmology, or even in astrophysics, you don't talk in terms of light years, you talk in terms of another unit called the parsec, which is about 3 odd light years, 3.26 light years to be precise. So Andromeda galaxy is located at a distance of about 700 kiloparsec. So in this movie, you will see the Andromeda galaxy appearing immediately after the first grid in yellow. And of course, after the last grid or the second grid, located at a distance of 1 billion light years, you will see a certain pattern in the sky that forms a crucial part of our story as we proceed. So let me play this movie. So let me restart this movie. I hope you're able to see. Okay, you can see that.
Yes.
You start from the Milky Way, and as you go further away, there are actually closer galaxies. We are not worried about that. They are relatively small, so-called satellite galaxies of the Milky Way. As you go further, notice this is the yellow grid I mentioned, which is at a distance of 1 million light years from us. As it proceeds, as the movie proceeds, from the left top corner, you will see the Andromeda galaxy coming into our view. These are small galaxies between us and Andromeda. It's largely empty space, but you will see on suitably small scales that is not quite true. Andromeda galaxy coming into view at a distance of about 2 million light years. And as we go further and further away, the universe contains many, many galaxies. And as I said, the Slow and Digital Sky Survey looked at a few different directions of the sky. You will see the movie tries to swivel and show the distribution of galaxies in different directions. So there are many, many galaxies. It's largely empty space. You find that, initially there seems to be a large amount of clumpiness. Seems to be the extent of formation of galaxies seem to be dependent on distance, and it seems to depend on direction as well. But on a suitably large scale, you find that that is not true. The question of interest is, what is that large scale? So here, the survey, sort of swivels around the axis, around the origin based on Earth. And now, if you draw a sufficiently large circle in one of these directions, you find the distribution of galaxies is relatively uniform. And this is often referred to as the scale of homogeneity, that is, of the order of about 100 megaparsec or so. On these scales, what you find is that the universe is homogeneous and isotropic. That is, it contains almost the same amount of matter over these scales, provided you average over these scales. And it seems to, be distribution of galaxies seem to be the same in which, all the different directions of the sky. Of course, we haven't observed all the directions of the sky, perfectly, but whichever direction we have been able to observe, I hope it is clear from this SDSS survey that the distribution is homogeneous and isotropic, and you begin to see these pattern of what are called as the anisotropies in the cosmic microwave background in green, yellow, red, and blue. This will form a crux of the story in due course of time. So what is the lesson we have learned? We find, let me close this and get back to my slide. This suggests that the universe is homogeneous and isotropic on suitably large scales, as I said, of the order of 100 megaparsec or so. This proves to be convenient for us to examine the universe theoretically. On these large scale, the universe, the Newtonian gravitation is inadequate to describe the universe, so one needs to turn to general relativity. General relativity is a very nonlinear theory, and if you have ever encountered nonlinear systems, you will immediately know that it is difficult to obtain exact solutions. However, if you can treat the nonlinearity as a small deviation from a linear equation, linear equations are easier to solve, and we can solve the perturbations as deviations from this linear system. This is what one does theoretically in cosmology. We treat the universe, though it looks clumpy on small scales, observations suggest that it is homogeneous and isotropic on large scales. So we assume by hand that the universe is homogeneous and isotropic, and we treat any deviations from homogeneity as a perturbation, and we try to understand how the perturbations grow. Of course, this has to be confirmed by observations. We will see that the amplitude of what are called the anisotropies in the anisotropies in the cosmic microwave background are indeed small at very early times in the universe, which allows us to carry out a consistent perturbation theory. So let me repeat. We find that the universe is homogeneous and isotropic on large scales. To make it theoretically amenable, we assume that the universe is homogeneous and isotropic. This is referred to as the background universe. Our goal is to understand the background universe, where the densities of matter present in the universe is not dependent on space, it depends only on time. So now the next question is the universe evolving? Is it changing with time? Well, as we see around us, it doesn't seem like it is changing with time, but it's indeed happening. But since the time scales of change is much larger than the human time scale, we are not able to perceive it easily. So how do we see that the universe is changing with time? One way is to it manifests itself in the so-called redshift of various galaxies. What has been plotted here is the spectra of different galaxies. What I want you to appreciate is that these galaxies are located at different distances. The one in the left top corner maybe is our own galaxy, for instance. The one on the top right corner is a galaxy slightly further away, and the one on the bottom left corner is somewhat further away, and the spectra on the bottom right corner is from a galaxy which is the farthest from us. Many of these galaxies exhibit spectra which are very similar to each other, and to a trained astronomer, for a trained astronomer can immediately recognize what these absorption and emission lines in these spectra are. And you can immediately see whether there is any pattern in the spectrum. One of the things that is found is that as you observe further and further away galaxies, the spectra are shifted towards the longer wavelengths, that is the red end of the spectrum. And the extent of redshift of a certain specific line, right, is indicated by the horizontal red arrow here. This further away galaxies exhibit a certain redshift. This is, they say, the spectrum of a star and of a galaxy. This is a galaxy which is a certain distance away. A farther away galaxy exhibits a larger redshift. Here is the redshift of even a galaxy which is even farther away. And in fact, this is very clear from the spectra of so-called quasars, which is displayed here. You can see that the pattern of these spectra are very similar to each other, and the redshift is indicated here. As you go upwards, the redshift is increasing, and this blue line, for instance, the first blue dotted line, vertical line, is the Lyman alpha line that you may be familiar from the transitions in hydrogen. And as you can see, these happen to be farther away, quasars which are farther and farther away, and their spectra seem to shift constantly towards the red end of the spectrum. What does it imply? Well, one reason they may be, redshifted, the spectra may be redshifted, is because of the fact that they are moving away from us. If you think it is Doppler effect, you can attribute a velocity based on the extent of redshift, which is plotted on the y-axis here in both these figures. On the x-axis, you have a distance to these galaxies indicated in units of parsecs on the left and megaparsec on the right. On the left is the original so-called Hubble data, which was put together in the late 1920s. Okay, and what Hubble had found, he managed to draw a straight line. He fitted a straight line to this data, and he had determined the slope of this. And he had found the slope to be 53 kilometer per second per megaparsec. So evidently the slope is velocity by distance. That is expressed as kilometer per second per megaparsec. What it means is that two galaxies which are separated by a distance of about a megaparsec are moving with respect to each other with a velocity of 530 kilometer per second. This is the first so-called cosmological parameter that we are encountering. I hope you appreciate this slope has dimensions. Kilometer and megaparsec has the same dimensions, so this slope has dimensions of 1/2. Now what it implies is that you can think of a collection of galaxies which are going away from each other. Imagine you have created a movie like this and you run this movie backwards. What it means is that at a sufficiently early time, all these galaxies seem to be on top of each other. This time when they were supposed to have been on top of each other, is referred to as the Big Bang, when all the galaxies seem to be sitting on top of each other. I'll make some corrections to this picture as I go along. The important point to note is that from this observed value of 500 or 530 kilometer per second, I can estimate a duration of time. It so happens, I will leave it as an exercise, this happens to be a few 3 to 4 billion years old. And this was the problem with the original Hubble data, because there were elements known on Earth which had a time scale, half-life much larger than this time of few billion years. On the right is a modern Hubble data, and the original Hubble data is indicated in red. You can see how further away we have gone in distances, and you can see the straight line, the linear relation between velocity and distance holds even to larger distances. And in fact, the modern value quoted is somewhere between 68 and 72. You may have heard there is something called the Hubble tension. There is a huge amount of discussion about what is the actual value of the Hubble constant or the Hubble parameter. The Hubble parameter today is referred to as the Hubble constant. It's somewhere between 68 and 72 kilometer per second. And if you invert this slope to obtain a time scale, you get a time scale of the order of 13 to 15 billion years, which is roughly considered to be the time scale of a universe today. And why is there this uncertainty? Why did Hubble get such a large value? Why is there an uncertainty today? Because the challenge is in determining the distance to these galaxies. It still poses a challenge. There is huge debate going on about this so-called cosmological distance ladder. There are various efforts on to, constrain this Hubble parameter better and better. So what is its implication for the universe? Well, I mentioned that these galaxies seem to be moving away from us. It seems to give this impression that we are fixed and these galaxies are running away from us. That's not quite so. This is just a manifestation of the fact that the universe is expanding. One way of visualizing this expanding universe is to think of galaxies as these yellow dots which are stuck on the surface of a balloon, or which are, scribbled on the surface of a balloon. And if you inflate this balloon, the distances between these galaxies increase with time. And you should understand this is just a two-dimensional representation of a three-dimensional expanding universe. You should not imagine that the universe is expanding into something. The universe itself is expanding, which means the distances between any 2 points in the universe is constantly increasing with time. One of the consequences when you study the evolution of photons in such an expanding universe, this is called a geodesic equation in general relativity. And if you solve for the geodesic equation describing a photon, governing a photon in an expanding universe, you will immediately find that if I leave a photon in the universe, its frequency decreases with time. It is this decrease in time of the frequency, that we see as redshift of these spectra of these galaxies. Photons take time to propagate from one of these red dots to another red dot. In this artist's impression, there is an effort to show that the blue photons at an early time, as the universe increases in time, changes red. And this is just a consequence of general relativity, and it is due to the expansion of the universe, and it is not actually due to Doppler effect that you are familiar in special relativity. So what do we know about the universe? Let me briefly summarize what we have learned until now. The universe is homogeneous and isotropic on large scales, and it seems to be expanding today. What else do we know about our universe? Why do we believe that the universe started in a hot, dense state, as the title of the Big Bang Theory sitcom says? We evidently have matter in the universe, but what else do we have in the universe? There is radiation. You see the radiation from all the stars. What has been plotted here is the intensity or the energy of radiation in the universe on the y-axis, plotted as a function of wavelength. There are many, many contributions to the radiation in the universe. Some of them are due to stars. But what you notice is that there is a peak. You can see around this point here in what is known as the microwave region of the electromagnetic spectrum. It is this so-called cosmic microwave background which contributes the most to the overall background radiation. Let me repeat. So there are various sources of radiation. Amongst this, the most dominant contribution to radiation is something known as the cosmic microwave background. What we find is that independent of which direction of the sky we turn to, there is this radiation in the microwave region of the electromagnetic spectrum which seems to be arriving at us. What else do we know about the cosmic microwave background? Well, it proves to be extraordinarily thermal. It is possibly one of the most perfect Planck spectrum that you will ever observe. In this curve, where you have plotted the intensity as a function of frequency, this is the famous Planck distribution that you have heard of many a time. This was a spectrum measured by Kobe. I should make a couple of historical remarks. The cosmic microwave background was first observed in 1965. This was a spectrum that was taken in early 1990s by this cosmic background explorer satellite, We will encounter Kobe again as we proceed with our talk. And something which I need to emphasize, the temperature of this spectrum corresponds to 2.725 Kelvin. And importantly, this error bars that have been plotted on the graph have been amplified 400 times so that, it can be seen in this figure. I hope you appreciate this is a remarkably perfect Planck spectrum corresponding to a fixed temperature. Now, the universe contains matter. It contains radiation, primarily in the cosmic microwave background, which we will hereafter refer to as CMB. So what are its consequences? Well, one can show from general relativity the following, that the energy density of matter, goes as 1 over volume. As I said, one can use in general relativity one can show that the energy density of radiation goes as 1 over v power 4 by 3. In other words, as the volume decreases, the universe is expanding. As you go back in time, the volume decreases, the energy density of radiation grows faster than matter density. As a result, at very early in the universe, you have the density of radiation dominating that of matter, and therefore you refer to this as the radiation dominated epoch. At later times, matter dominates, you refer to this as a matter dominated epoch. So where does the CMB come from? Well, this picture here, this image here, tries to describe that. On the left corresponds to early times, and this red, the yellow smeared object represents the radiation fluid. These large red balls, I hope you recognize, are protons, and these small green balls are electrons. The large green balls are neutrons. I hope you appreciate that these isolated red balls, large balls, are essentially hydrogen nuclei. This is a helium nuclei. So what happens? At very early in time, the energy density of radiation is very high. Therefore, whenever an electron tries to combine with a proton and form a hydrogen atom, the photon knocks it off, leaving them completely ionized. Both the hydrogen and the helium nuclei are ionized. But as the universe expands, that is, as you go towards the right, the temperature cools down, and as a result, the number of photons present also decreases with time. In fact, what you need to compare are two scales, time scales, one corresponding to the interaction rate of the electrons and the photons, which is determined by something known as Thomson scattering, which you may have heard of, and another is the expansion rate of the universe. There comes a time in the universe when the reaction rate falls slower than the expansion rate. And as a result, what happens is that the photons, in other words, the photons do not have sufficient energy to knock off the electrons, which go on to form hydrogen atoms here. As you can see, the electron here has been described as a cloud around the nucleus, and here you have a helium atom. So they go on to form these atoms. These photons do not have enough energy, as I mentioned, to knock off these electrons, and they start, as you can see, streaming freely towards the right. And we are located far away on the right, and it is these free streaming photons that hit our detectors and register as the cosmic microwave background. And this is referred to as the decoupling of matter and radiation. Essentially, matter and radiation cease to interact, and these photons come and hit our eye. And this is supposed to have happened when the universe was, much hotter. Remember, the temperature today of the cosmic microwave background is about close to 3 Kelvin. This decoupling is supposed to have occurred when the universe was about 3000 Kelvin or so. And it is this what we observe as the CMB. There is a nice example which illustrates this idea very well. What happens when you see this cloud here in the sky? You have photons which are trying to escape this cloud, which consists of water molecules primarily and a few other molecules, but its mean free path is very small. But when it comes close to the edge of a cloud, its mean free path suddenly increases to a very large value, and it is these which come and hit our eye, and that is why you see the cloud in the sky. In the very same fashion, you are located here, you are observing the sky in all different directions. What happens as you make, I hope you realize as you see deeper and deeper in the sky, you're looking at the time of the universe when it was older and older, because photons take a finite amount of time to reach you. And there is this last scattering surface, very much like the cloud on the left here, when the photons is supposed to have escaped and reaching, eventually coming and hitting our detectors. And this surface is called the surface of last scattering. We have been able to measure this, the temperature of the CMB to greater and greater accuracy. We have also been able to measure the temperature of the CMB in different directions of the sky, and it is usually presented in the following fashion. Using a projection, you can transform from the theta phi coordinates on a globe to a projection onto an ellipse in this, and where you can represent the different temperatures on the surface of the earth. In a similar manner, you can project the last scattering surface onto an ellipse in the following fashion, and these correspond to different directions, the temperatures in the different directions of the microwave sky. Here is the extent of isotropy of the CMB. What you find is that as you look at different directions in the sky, you see very small deviations in the temperature of the CMB. But the thing is, they are 1 part in 10 power 5. Remember, you are seeing, when you observe these CMB anisotropies, you are observing the universe as it was at a very early stage. What it means is that the change in the temperature in different directions of the sky is very small, which in turn indicates that the deviation in the energy density at such early times was very small. If rho is the energy density and delta rho is the deviation in the energy density, delta rho by rho in radiation is 1 part in 10 power 5. This is important. This is another observational confirmation of the fact that this division, the theoretical division of a universe into a homogeneous or an isotropic part, where there were small anisotropies or inhomogeneities superimposed on this homogeneous and isotropic part, is consistent with the observations. In other words, the CMB anisotropies, or the smallness of the CMB anisotropies, confirm that this division is accurate. We have been able to measure the anisotropies in the CMB with increasing precision. On the left is the CMB sky as originally observed by Penzias and Wilson in 1965. You see this pattern in the middle. This is supposed to be emission from our own galaxy. You should ignore that. Otherwise, the temperature is almost the same in all different directions. It's the same in different directions of the sky. But once you start observing the deviation at the 5th decimal place, you start seeing deviations in the temperature, and this has been measured with increased resolution, first by Kobe, the cosmic background explorer, then by something called WMAP, and more recently by Planck. Now, so this is the reason why we believe that the universe began in a hot, dense phase. I hope you are also able to appreciate the fact that these anisotropies carry pristine information about the physics of the very early universe. Therefore, by measuring these anisotropies to greater and greater precision, we are able to understand the universe, how it was at very early times. So this part covers the hot Big Bang background. I don't know how I'm holding with time. I think I'm doing poorly. How much more time do I have? I need to move at a suitable speed.
We have about half an hour more, but
okay.
Here and there shouldn't be an issue.
Sorry?
10-15 minutes here and there shouldn't be an issue.
Okay, so I will try to cover in about 20 to 30 minutes. Okay?
Yeah, thank you.
Thank you. So Why do we need inflation? Well, we seem to have a hot Big Bang model which seems to be able to explain the presence of the CMB. Why do we need inflation? The problem arises due to this point. So you have a Big Bang, you have this epoch of decoupling, which is followed by this epoch of matter domination. And you can ask whether different regions in the sky, in the CMB sky, are causally connected by this time, when the photons decouple from matter. When you ask this question, you find that any patch in the sky, which is more than 1 degree in the sky, are not causally connected within the hot Big Bang model, where you have an epoch of radiation domination followed by an epoch of matter domination. These white patches, as I have written here, represent the size of the causally connected regions in the CMB sky within the hot Big Bang model, and this is called as the horizon problem. I hope you appreciate the point. What it implies is that we find the temperatures in different regions of the CMB sky, even in antipodal points of the CMB sky, have virtually the same temperature, roughly 3 degree Kelvin today. However, any two regions beyond a single degree in the sky are not causally connected, and it would have been more natural to find, different regions of the sky to have different temperatures. But that is not what we find. We have the entire CMB sky having almost roughly the same temperature. There is another way of stating this horizon problem. You can draw a light cone. I hope you have encountered light cones in special relativity. In general relativity, you have to work with certain time coordinates, in order to ensure the light rays travel at 45 degrees. One such coordinate system has been chosen here to illustrate these diagrams, to illustrate this phenomenon. What has been drawn, we are here today, corresponding to something called redshift equal to 0. Remember, stars in our own galaxy do not exhibit redshift, and therefore Z, the redshift is 0. At an early time, photons decouple from matter, which is where we observe the CMB coming from. This is the last scattering surface, and this is supposed to have been a Big Bang. You have the radiation dominated era here and the matter dominated era here, and this is, say, the WMAP satellite, which is observing the CMB anisotropies. So what do you find? You can draw a forward light cone, invert this blue light cone. Then what will you have? You will have a light cone which is just as big as this. In other words, there may be many such light cones that can be squeezed within this ellipse here. In other words, as I mentioned in the previous slide, different regions of the CMB sky haven't had time to interact by the time of decoupling. This is essentially the challenge with the hot Big Bang model. Hot Big Bang model is not able to explain why the CMB sky has roughly the same temperature. How do you overcome this? Well, it is very simple. If you, instead of the Big Bang starting here, if you are able to push Big Bang to an earlier time, it is clear that I can draw a forward light cone which is as big as the backward light cone here, so that the forward, you can ensure that even extreme regions of the CMB sky are causally connected. And this is possible provided you have a period of accelerated expansion. I mentioned at the beginning of my talk that you cannot have accelerated expansion with matter and radiation. Matter does not have any pressure at all. Radiation has pressure of rho by 3 and rho is sigma T power 4. Therefore, it is a positive definite quantity. So if you require inflation, matter and radiation cannot achieve it. You need to turn to some other fields that are present in high energy physics. Why high energy physics? Well, inflation is supposed to have happened very early in the universe. As we discussed, the energy density of radiation goes higher and higher as you go back in time closer to the Big Bang. Recall, according to Stefan Boltzmann's law, the energy density of radiation is proportional to T power 4. So if the energy density of radiation is high, the temperature of the universe is also high. This is why we refer to it as the hot Big Bang model. So there is another way of representing this horizon problem. What has been plotted are two scales that are present in the universe at all times. One is the size of an object of your interest in cosmology, and another is called the Hubble radius. It is not difficult to understand the Hubble radius. It reflects the rate at which the universe is expanding. In other words, very loosely, it reflects the speed at which the universe is expanding. Okay, and you can construct a length scale associated with this. Okay, by dividing with a suitable quantity. Okay, and then you have, as I said, the size of an object, which is plotted in blue. Because the universe is expanding, the size of the object, loosely put, also increases with time. It is called the wavelength of a perturbation. Okay, and then there is this Hubble radius, which is plotted in red. If you don't have an epoch of inflation, what happens is that this blue line will eventually leave this red line as you go back in time. In other words, the causally connected region is represented by this red line. This blue line, you can think of some sort of waves or perturbations that are introduced in this universe. You can think of a wave which is larger than the size of the universe. Evidently, it cannot influence anything in the universe. It has to be inside the universe to influence it. And that is what inflation achieves. Inflation ensures, during inflation, if you have a period of accelerated expansion, you can show this Hubble radius is roughly constant, and this wavelength of these perturbations can be brought inside the Hubble radius. And I will talk about some quantum fluctuations as we go along. These quantum fluctuations originate at such early times, and which is what is responsible for the structure, as I will try to describe over the next few slides. What I wanted to appreciate is that the time of inflation is very brief. As you can see, what has been plotted is time on the y-axis. Okay, the early time correspond to a point up in the y-axis. The Big Bang is indicated this bright white dot. Okay, and on the x-axis you have length, and this in some sense reflects the size of the universe. What you notice is that in a very short span of time, at around a time scale of about 10 power minus 35 seconds after the Big Bang, the universe increases in size by order of about 10 power 30 or so. That is why it is referred to as inflation. It inflates our universe tremendously through a period of very rapid expansion. And how is this inflation achieved? Well, I mentioned that that matter and radiation cannot drive inflation. You need to turn to some objects called scalar fields. There is a nice way of imagining the behavior of a scalar field in an expanding universe. You can think of it as a ball rolling down a potential that you would have encountered in classical mechanics, albeit with one minor complication. Well, there is friction exerted on the ball because of the expansion of the universe. This essentially, this picture you can understand from studying the equations describing the scalar field in an expanding universe. So think of a ball which is exerted by a certain friction as it rolls down the potential. What one finds is that as it rolls down, initially, if you have a very nearly constant potential, the ball will hardly have any velocity, and therefore one can show in such a domain, it's often referred to as slow roll inflation, because the ball is not rolling, the field is not rolling fast enough. Okay, and there are many potentials which will admit this behavior. The field rolls slowly and it can lead to an epoch of inflation. As it rolls down the potential, what happens is that very close to the bottom, inflation naturally ends. And where do you turn to these potential from? Well, in what direction, or where do you look for these potentials? You look for them in high energy physics, and high energy physics contains many scalar fields, and there are many potentials. You have a variety of potentials to choose from to achieve inflation. And what else does inflation do? Remember, we said we need inflation to overcome the horizon problem. But what happens is as follows. Inflation, as I have been describing, is typically driven by scalar fields. I'm sorry about that. Okay, and these scalar fields in high energy physics, you may learn in a quantum field theory course later, they contain quantum fluctuations, which means that they have intrinsic fluctuations which are unavoidable. In fact, it is these quantum fluctuations which are responsible for the cosmic anisotropies in the cosmic microwave background and the eventual formation of galaxies. What I'm going to do is that I'm going to play two movies which tries to illustrate this phenomena. Just bear with me. I'll try to share the movie. I hope you're able to see this now. Yeah, I can see that you're able to see. So think of a smooth universe which contains nothing. It's very smooth. And these bubbles that fall on this correspond to quantum fluctuations. Okay? These pebbles which fall on this water correspond to quantum fluctuations, which are inevitable. And the universe contains, these quantum fluctuations correspond to many pebbles falling on top of this. And they create a pattern which correspond to the inhomogeneities. We have a smooth universe. These fluctuations, which are intrinsic to quantum fields, introduce these inhomogeneities, that is deviation from smoothness in the energy density of radiation, which is what we eventually see as the CMB anisotropies in the CMB sky. Let me just illustrate this for you. So you can see this pattern of anisotropies, and that are supposed to be responsible because supposed to arise due to quantum fluctuations in the early universe associated with the scalar fields. I'm going to show you another movie. Just bear with me. So what do you have? So these perturbations are actually amplified during the inflationary epoch, okay? And eventually the fluctuations in the CMB grow in magnitude. Apart from leaving their imprints as anisotropies in the cosmic background, they are eventually supposed to be responsible for the large-scale structure which see around us as galaxies and clusters of galaxies. I'll play another movie which illustrates this. Again, you need to bear with me as I try to present that. Okay, I'll start from the first. So you have the CMB anisotropies. A small part has been zoomed in. The universe contains nothing. There is no radiation other than the cosmic microwave background. Eventually the first stars form. This is referred to as cosmic dawn, and you will see they eventually go on to form galaxies and clusters of galaxies. You have a CMB sky as observed by the W map on this side here, okay? And here it passes through the galaxies and clusters of galaxies before it eventually comes and reaches the CMB detectors. So this is the picture one has, and in fact, just let me go back to the slides, just bear with me. So this is the picture one has, and by being able to observe the CMB with greater and greater precision, we are able to constrain the inflationary models. I'm not going to, for want of time, I'm going to skip the slides. As I already said, the anisotropies are being measured with greater and greater precision. There are two things that we are interested in when you try to constrain the physics of the early universe. This is slightly technical, nevertheless, let me go through it. Okay, you have something called the tensor to scalar ratio. What happens is that, apart from generating perturbations that eventually create you and me, they create something called gravitational waves that in principle can be observed from the pattern of the CMB sky. Pattern of the anisotropies. And the other thing we know is the power spectrum of the primordial perturbations. I have a perturbation or inhomogeneities in space. I Fourier transform this and I talk about the power spectrum in the Fourier space, and we know what the power spectrum is. It is almost scale invariant, it's almost flat with a small what is called a spectral tilt of ns, which is close to 0.96. And we yet haven't seen the imprints of gravitational waves. You may have heard about the story related to something called BICEP about a few years back, 4-5 years back, when they claimed to have seen it, that did not turn out to be true. And we are, still trying to detect the imprints of these primordial gravitational waves. If we are able to see that, we will be able to understand the universe at the highest energies which are impossible to be achieved by terrestrial accelerators. So this covers the inflationary paradigm. This picture that we have here, that I have presented over the last almost an hour now, is, has led to this so-called hot Big Bang model. You have a Big Bang where the universe expanded, soon after which the universe went through a phase of inflation when it expanded extremely rapidly. There were quantum fluctuations which led to anisotropies in the CMB, which eventually led to the formation of large-scale structure. So why do we need the bouncing universe? Well, the challenge is that there are many inflationary models. As I said at the beginning of the talk, it is not even clear whether we can rule out some of these models, and there are concerns that have been raised whether this inflationary paradigm that I presented is even falsifiable. This, led us to examine bouncing scenarios. What are these bouncing scenarios? Well, I have tried to explain in 2 or 3 points. Okay, you can ignore the third point. Okay. The first 2 points are, you should be able to appreciate from the points I have presented in the context of inflation. The bouncing models correspond to a situation where the universe does not go through a Big Bang. The universe goes through a phase of contraction when something called the scale factor, it turns out to, it comes down to a certain minimal size, so to say, before it transits to the current expanding phase. I had described as to how inflation allows us to overcome the horizon problem, how the forward light cone can be made as big as the backward light cone. It is very clear, if you have a very long phase of contraction prior to the big bounce, it is very clear that the forward light cone will be very big, and therefore it is able to solve the so-called horizon problem that I had described, which inflation was supposed to overcome as well. Okay. However, there are certain challenges. I will skip this point because it's a little technical. And the way you can visualize the bouncing scenarios is that, in this side, you have the current universe. Today is somewhere here. This corresponds to a very early epoch. Okay. The universe goes through a phase of contraction, and the space-time is always classical. There are concerns whether there will be so-called quantum gravitational effects that will come into play very close to the Big Bang or the Big Bounce. Okay, in these scenarios, the space-time is always classical. In other words, gravity is described by Einstein's general relativity, often so. Okay, and universe goes through a bounce, which is illustrated by this red band, and then it starts with a phase of expansion. But there are certain challenges in constructing bouncing scenarios. Before that, let me explain how do you overcome the horizon problem in the bouncing scenario. Recall this picture that I had plotted here. I had plotted, something referred to as, if you think of waves in the universe, which we refer to as perturbations. The wavelength of these waves changes with time in this manner. It is always proportional to the way the universe changes with time. And I had plotted something called the Hubble parameter, which is essentially the rate of expansion of the universe. And I had explained how, if you have an epoch of accelerated expansion, the wavelength of these waves can be smaller than the size of the universe. Well, the same thing happens in the bounce. I have plotted in a somewhat different way. Okay, this corresponds to the contracting phase and this corresponds to the expanding phase. You can show that if you have a very early epoch during the contracting phase, which is dominated by matter, you can show that this blue line is under the yellow line. I'm sorry, under the red line. Remember, the red line reflects the size of a causally connected region. The blue line indicates the wavelengths of these waves. The question is whether I can fit many wavelengths within the size of the universe at that time. And what one can show is that if you have an epoch of contraction, then at very early times, provided the universe is not undergoing accelerated contraction, these wavelength of these perturbations, the wavelength of these waves will be inside the causally connected region at that time. And therefore, you can in principle generate perturbations just as in the same manner I had described in the context of inflation. If you recall, you use scalar fields to drive inflation. The scalar fields contain quantum fluctuations, and these quantum fluctuations can be made to generate these perturbations. And that is what happens in the context of the bouncing scenario as well. Okay, it is a little technical for me to write down the equations involved to show how it is actually achieved. So what I'm going to just show is that, how these amplitude of these perturbations behave. And remember, I had introduced this quantity called the tensor to scalar ratio, which tells you how much of gravitational waves were generated in the early universe. I had highlighted in the context of inflation that they are always generated in the universe, and and there has been efforts to see what is the extent of gravitational waves generated in the early universe. On the left, I have plotted the evolution of the perturbations. What one finds is that as the universe contracts, 0 refers to the bounce. As the universe contracts, remember, I talked about these wavelengths which are inside the universe, but they eventually go out as during the contracting phase, as the wavelength of the perturbations go out very close to the bounce, their amplitude increases, and you can estimate what they are, and what their imprints on the CMB will be. One of the interesting results, what one finds is that, the so-called amount of gravitational waves that will be produced in this universe will be very small. If you had seen the figure earlier, the current constraints, restrict this quantity called R to be our 0.06. In some of the models we have studied, it will be extremely small. This R will be like 10 power minus 5 or 10 power minus 6. Another interesting problem we have examined, I will skip this slide, okay, for want of time. Another interesting problem we have examined is whether the primordial spectrum contains features. I had earlier indicated that the spectrum, power spectrum, is essentially the Fourier transform of the distribution of the matter in the universe in position space. And I had also indicated how well it is measured by the CMB. The typical spectrum I had, that you will get in an inflationary model is a black line as indicated here, something like this. In fact, we know the amplitude of the primordial perturbations to great accuracy because we know the amplitude of the CMB anisotropies. What one finds is that generically inflationary models lead to a scale invariant perturbation spectrum. This is something you will repeatedly hear in the context of physics of the early universe. We have been examining whether there are deviations from a nearly, scale invariant or scale free, that is absolutely independent of the scale. We have been examining whether there are deviations, and what one finds is that, if you introduce certain features, such as this, as described by this blue line, or as described by these oscillations in this red line, or described by, this small oscillation that you have in green line, we have been examining whether such features are consistent with the cosmological data. And they can be generated by various inflationary potential. I have not spent time on it. Okay, you need to introduce certain features in a smooth potential. I had described the inflationary potential earlier. Okay, and if you introduce some oscillations, for instance, you can get oscillations in the primordial spectra, and they are in fact proved to be more consistent with the data than a nearly scale invariant spectrum. The question is, Can you generate these in the context of bouncing models? This has proved to be a challenge. In a recent work, we have been able to show there are certain kinds of contracting phases. I had drawn this picture of the potential with the ball rolling in the context of inflation. I had said how you have a kinetic energy and a potential energy. If the kinetic energy is much smaller than the potential energy, you can have an epoch of inflation. What one finds is that if you have a contracting phase driven by a potential that is negative definite, and you have a case when the ball is rolling slowly, then what one finds is that you can have you can have a situation where you have extremely slow contraction. This scenario is called as the ekpyrotic scenario. You can have a slowly contracting phase, using the so-called ekpyrotic potential, which are negative potentials. And in such scenarios, you can generate features in the primordial power spectrum in bouncing scenarios in contrast to inflation. What I would like to emphasize is that generating these features, notice these features with a sharp drop or an oscillation or constant oscillations are very similar to these features that I had described earlier, which have been examined in the context of inflation. Okay, so these features can also be generated in bouncing scenarios. That was the last point. This was work from our group. Okay, that was the last point I wish to make, and let me quickly summarize with a very brief outlook. Okay, as I mentioned, inflation is a simple, effective, and compelling paradigm. But I had argued as to how it's very easy to construct an inflationary model, and in fact there is a profusion of such models, leading to the concern whether as a paradigm inflation can be falsified at all. And something I couldn't spend time on, it's a bit technical as well. There are various recent arguments which suggest that some of the standard popular models of inflation are inconsistent with string theory. It's called as the swampland. And there are other arguments which suggest that inflation cannot happen at very high temperatures or very high energies. Okay, and therefore we turn to examining the possibility of bouncing scenarios. What I did not describe is the challenge in constructing these models that we have discussed. They often require very strange kinds of fields to achieve bounces. Okay, and there are many theoretical issues which you are still examining, whether, I had mentioned as to how you need to turn to quantum gravity or a, model such as string theory to achieve bounces. The question of interest is whether these quantum gravitational effects are important near the bounds. These problems we are trying to address, and we hope to address some of them over the next few years. With those remarks, I will thank you for your attention, and I'll be glad to answer if there are any questions. Hi, guys.
Hi, sir. Yeah, we've received some questions in the YouTube comment section.
Okay.
One is, how does one explain the observation that the galaxies themselves are not expanding and the distance between galaxies is increasing? The whole universe isn't scaling up by a certain factor.
The point is that the galaxies are bound gravitationally, very tightly bound gravitationally. So there is no effect on them actually. Okay, so the galaxies themselves are not expanding. In fact, even a cluster of galaxies exert, sufficient gravitational forces for some of the galaxies not to, to exhibit even small extent of blue shift. Okay, so I hope I have answered your question. The galaxies are bound, tightly bound due to gravitational forces, due to local gravitational forces. As a result, they don't expand. It is the universe which is expanding.
Okay, so is it possible that at some point, due to the expansion, the distance between the constituent atoms would expand beyond the range of electromagnetic interactions?
The point is that the electromagnetic force is much more stronger, right? So you don't have to fear that the atom is going to expand due to this.
Okay. And how did the anisotropy then lead to the current isotropy?
No, I didn't. Okay. So the anisotropies, once they are present, you cannot erase them. I was careful to say those anisotropies are still present. Okay. I hope you appreciate this point. This is a little subtle. The universe is anisotropic today, but it depends on the scale at which you observe. Okay, it is easier to explain in terms of homogeneity. I was illustrating the distribution of galaxies, right? Evidently, as we see around us, the universe looks very clumpy, which means it is not homogeneous. But on a suitably large scale, in other words, I place a sphere at different parts of the universe. If the size of the sphere is small, you can imagine, the densities will vary considerably. But if you keep increasing the size of the sphere, there comes a certain scale when the universe is indeed homogeneous. And that scale is the cosmological scale. I had mentioned a scale of the order of 100 megaparsec over which the universe is homogeneous. So what you see is that the large scales are still to become inhomogeneous. They will eventually do in the future. Okay? It just reflects the fact over those scales, the inhomogeneities haven't grown so much. I don't know whether I have been able to answer that question, but I can repeat if the question is asked differently.
So I think that answers the question.
Okay.
Given that the CMB is a remnant radiation from the Big Bang, is there a time scale possible after which this radiation would not be detectable anymore?
The radiation will just go down asymptotically. In fact, you can show that the temperature of the radiation goes as 1 over the size of the universe. So it will go to 0 only asymptotically. It will reduce slowly, but it will reduce on such large time scales, much larger than the human time scales.
Okay. The next question is it possible to address a t not equal to 0 in bouncing scenario from the minimum length scale theories of quantum gravity?
So the thing is, the moment you try to take into account, okay, let me track back. We still don't have a workable or a viable quantum theory of gravity. So if you have such length scales, you need to introduce them in some ad hoc fashion. So what we try to do is that in our models, these are what are referred to as classical bouncing scenarios. Our energy densities are always much smaller than the Planck values. Therefore, there is no concern about quantum gravity modifying the physics we are discussing. So these are referred to as classical bounces. They are easy to discuss. There are quantum bounces that are also considered, but that is strongly depend on the kind of model of quantum gravity you may have.
Okay. So the next question is that inflation is often debunked as unfalsifiable, as many parameters can be tweaked to arrive at a desired outcome. So does the Big Bounce theory also have a similar problem with it?
So you have to understand when we refer to, historically the name Big Bang was given by Hall to make fun of the theory. He was proposing the steady state theory. Somehow it stuck. You have to understand when we refer to the Big Bang itself, we are not able to explain. The reason being we use general relativity to explain our universe, and general relativity is expected to fail close to the Big Bang. And as we just discussed a minute or two back, quantum gravitational effects are supposed to take over. So whether Big Bang happened or it has to be replaced by a big bounce, if it goes to, as I said, in our scenarios, we ensure that we don't reach quantum gravity scales. So quantum gravity is not, affect our scenarios at all. But it is not clear, if you stick to conventional physics, what happened close to the Big Bang. And if you allow the energies to go indefinitely higher and higher, our theories will fail. And you need a new theory to exactly understand what happened.
Okay, sir. Since the CMB is the redshifted radiation from the decoupling of matter and radiation, does that mean that we cannot observe radiation from beyond the CMB?
So it's a good question. Well, you cannot observe radiation, photon radiation. You can, in principle, observe neutrinos, which are supposed to have decoupled at a time prior to the CMB. So if you have if you are able to detect neutrinos, it's a challenge to detect neutrino. Just like you have a cosmic microwave background, you also have a cosmic neutrino background, which is supposed to be at a temperature of about 1.9 Kelvin or so. So in principle, if you have neutrino detectors and you turn your detector all directions of the sky, you will be able to observe the universe as it was prior to this epoch of photon matter decoupling. You will be able to see the last scattering surface of the neutrino matter decoupling. And similarly, there will be gravitational waves produced in the early universe. Okay, and if you are able to observe something called the stochastic gravitational wave background, and there are many efforts to see whether we can see different sources of gravitational waves which are not confined to, say, merging black holes. We are talking about a background of gravitational waves in a manner very similar to background of photons. If you are able to detect those gravitational waves with your detectors, the challenge in detecting them is that they are very weak. They leave very small imprints on your detectors, which we are not able to see. But in future, if you are able to see them, a neutrino background and eventually the stochastic gravitational background will give you a picture of the universe as it was at extremely early times, much prior to this epoch of decoupling which led to the CMB.
So there was a follow-up to that. Can we observe behind the last scattering layer?
That's what I said. You cannot observe using photons, but you have to turn
EM radiation, right?
Well, in the sense of the EM is still participating in the interactions. Okay. Behind the layer, think of the cloud, right? When you see the photon, you see at the edge of the cloud. Okay. So you see the pattern on the edge of the cloud. You don't know what happened inside the cloud.
I see. Yeah.
Okay, so what happens is that, so you see from the last scattering surface, well, in principle, you can evolve all the equations to see what happened to the photon prior to that. That is how, in fact, we constrain inflationary models, etc. Okay, but you don't directly see what happened at surface. So, as I said, you need to turn to other backgrounds, like the neutrino and the gravitational wave background, to see how the universe as it was at that given epoch.
So what do the Big Bang theory and the Big Bounce theory differ with respect to the future evolution of the universe? And
the future is in the sense of, look, you need to understand that when we replace Big Bang with the Big Bounce, we are just changing the evolution of the very early universe. Since we have such observations at late times, your Big Bang bounce theory should match other things which of the Big Bang theory at later times, because you have strong constraints on them. For instance, you are changing the physics at very high energies. The physics at low energies or at late times should remain the same. Otherwise, your theory will not be consistent with the observations. I hope that is clear.
Yeah, this is the final question, sir.
Sure.
In a sense, when we address the Big Bounce theory, aren't we just skirting the topic of the very first beginning?
Well, we are replacing it by something else called the Big Bounce. We are not skirting it, we are squarely dealing with it. Whether it is correct, whether it is right, whether our models are theoretically well motivated, these are challenges, but one has to explore them. So we are certainly not. In fact, I would say that, look, you have to understand, inflation does not resolve anything related to the Big Bang.
Right.
Okay? Inflation is something that happened post to the Big Bang. I didn't say big inflation versus Big Bang, versus Big Bounce in the title, because Big Bang versus Big Bounce sounded more attractive. Okay? So this was more of a talk of inflation versus Big Bounce as to what caused the primordial perturbations.
Okay.
Right? So inflation does not answer the Big Bang. In fact, we don't have something which tells you what happened close to the Big Bang. I shouldn't say we don't have. There are models, something called in loop quantum gravity, and there are some models in string theory which can actually lead to bounces. There are some similarities to the bounces that we discuss here. Okay, there are models But whether there are clear predictions which are confirmed by observations, no.
Okay. Thank you, sir. That was a really enthralling talk. It was great having you with us. Thanks a lot.
Thank you. Thank you for the opportunity. I'm sorry if it got a little technical at times. I hope you are welcome to catch me sometime and ask me more questions if there is interest.
Thank you.
Thank you for the opportunity. Bye bye.
Thank you, sir.